Hello everyone, welcome to Slant, and I will be the host today. In this webinar, our Wi-Fi experts Dr. Doron and Oren will introduce the latest Wi-Fi technology and answer questions after the presentation. So we are glad to hear your questions. Please write down or you can discuss them directly in the discussion session. In addition, today's webinar will be recorded and published in a few days. Okay, without any further delay, I'm now going to turn over to Dr. Doran to get started. So, Dr. Doran, if you are get ready, please start it. Thank you.
Thank you very much, Yao. Thank you very much. Let me just share my screen. Can you see my screen? Wait.
No.
Wait a minute. I think now it will be okay.
Yeah, it's starting.
How about now?
Yes.
Great.
Great. So, can you see my pen?
Yes.
Okay. So, perfect. So, hi guys, I'm Doron. I'm CTO Wi-Fi of Huawei's Datacom product line. And what I want to do with you today actually split into two parts. I'll start by telling you a little bit about myself, but then I'm going to give you a quick introduction into the key features of Wi-Fi 7, but I will try to do that like from what I think a customer perspective, yeah? So what are the actual features, what are the main features, and then immediately I will try to explain what is the benefit, what is the gain for customers, from the customer's point of view into these features, why, well, we spend the time to develop these features at IEEE standardization. And after I do that, I want to give you like a glimpse into the next generation of Wi-Fi. This is Wi-Fi 8, and I want to give you an example. This is an example of one of the hottest topic in current Wi-Fi 8 standardization, which is coordinated beamforming. And this presentation is going to be based on a presentation I gave at a very high-profile conference organized by Professor Shlomo Shammai Shitz with a Shannon Award winner. It's like a Nobel Prize of the information theory. And after I will finish my part, then Oren will dive much deeply into multi-link, which is one of the key features of Wi-Fi 7, and also what great things we can do with multi-link. And you will see we can do totally different things, from increasing capacity to increasing reliability to reducing latency, and so on. So a little bit about myself. So I was the CTO of Runcom Technology. This was the company that invented OFDMA. So I was lucky enough, to be there where all this OFDMA revolution happened, and I was responsible for the first OFDMA MIMO chipset in the world. This was a WiMAX mobile station Wave 2. Then I had my own company working mostly on MIMO cores, worked with all the big players like Qualcomm, Intel, Broadcom. I joined Huawei in 2012, so already 11 years, and currently I'm the CTO Wi-Fi of Huawei's Datacom product line. I lead a team in Israel and another team in China, focusing on all the big aspects, technological aspects of Wi-Fi, MIMO, OFDMA, chipset standardization, and so on. From the research perspective, so I've been teaching a graduate level OFDM MIMO course at Tel Aviv University. This is one of the top 3 universities in Israel for the last 17 years. And more exciting, so for the last 2 years, I've been teaching at Beihang University in Beijing. Amazing experience, totally different than teaching in the West. I wrote 2 books, around 30 papers, and over 100 patents, and everything is about wireless communication. So I consider myself a wireless enthusiast. Yeah, everything is around wireless communication. So let's start and discuss a little bit about Wi-Fi 7. So from, let's say, IEEE standardization point of view, so draft 4.0 has already been released very recently, a few days ago, which 4.0 means that essentially the standard is mature and we only have very small comment collection going on, but essentially the standard is fixed, it's closed. The main features for Wi-Fi 7 are first 320 megahertz bandwidth. And again, I think everybody understands, you don't have to be like a wireless communication engineer to understand that if you're doubling the bandwidth, then you're of course doubling your capacity. The second feature is 4K QAM, so I will discuss this also a little bit. And of course, this also used to increase capacity going from 10 to 12 bits per second per hertz. The third one is preamble puncturing and multiple RU, which can be viewed as the OFDMA on steroid. And the last but not least, probably the most important one, is multi-link, which allows the station to communicate with an AP simultaneously on multiple bands. And I'll discuss a little bit, and then later Oren will have a much deeper dive into multi-link as a key feature of Wi-Fi 7 and the advantages that we can gain from it. So let's start with the simplest one. So as I said, 320 megahertz, while 11C and 11AX Wi-Fi 6 did not increase the bandwidth. It was still 160 megahertz, and I think the community understood that it is time to increase the Wi-Fi bandwidth to 320 megahertz. So it's a huge bandwidth, and as I said, you don't have to be like a wireless engineer. You double your bandwidth, so now everything is doubled, and of course you can also double your throughput, yeah, and definitely in the 6 gigahertz. 320 can be used either in a non-OFDMA like the traditional way and also in OFDMA. So you don't have to imagine that I'm giving all of this huge bandwidth at the same time to only one station. I can work in OFDMA and I can communicate with multiple stations. Each one of them is going to be allocated with a different frequency band, and I will discuss how puncturing can be used to turn it into like OFDMA on steroids. So the FCC, you know, in the Wi-Fi 6E allocated 1200 megahertz, like in the US and in other places for the 6E, and in Europe we have the UNI 5 480 megahertz, which means that we can either use this guy or we can use this guy, and both will be contained in the UNI 5. So 320 megahertz, again, immediately if you're thinking about applications that require very large bandwidth and so on, then you got it through the 320 megahertz, and this is like an improvement from the 160 megahertz of Wi-Fi 5, Wi-Fi 6, Wi-Fi 6E. So this is the first one. So if we're talking about increasing the throughput, then what goes hand in hand together with the 320 megahertz is the move from maximal modulation of 1K QAM to 4K QAM. And if in 1K QAM we can have like 10 bits per second per hertz, like each QAM can carry 10 bits of information, then naturally if you're moving from 1K to 4K, you increased your throughput by 20%, because now you have 12 bits per QAM. So 12 bits per QAM immediately increased by 20%, and these are extreme scenarios of the high SNR. Naturally, if you want to work at such high SNR, you need to make sure that your transmitter error vector magnitude, EVM, is much better and definitely increased by at least 3 dB. So when we're moving to the 4K QAM, we set the EVM on minus 38 dB, and all of Huawei's access points and devices support this amazing EVM. And again, you can imagine this is the baseband work, this is the RF work, this is like a system level target to reach the minus 38 dB of EVM, but we're definitely there. So a question that I usually get from customers is, you know, why do we need 4K QAM? I mean, in advanced Wi-Fi, definitely Wi-Fi 7, we work with MIMO. I will discuss MIMO a lot in in the next part of this lecture, of this discussion. So why do we need to insist on working with 12 bits per second per hertz with 4K QAM on very high SNR? And the answer for that is that 4K QAM is actually designed for the near line of sight scenario. So imagine that the access point and the station are very close. And this, of course, happens like in the living room, in your home, if it's not enterprise, if it's residential Wi-Fi, or like in a conference room. And so you can find yourself quite close to the access point. When you're very close to the access point, you have a very strong line of sight component. Strong line of sight component plays two roles. One of them, SNR is very high. This is great. But on the other hand, when the line of sight component is very strong, it means that your MIMO matrix is degenerate. It means you don't have good MIMO. So, I mean, the number of spatial streams that you can work is either 1 or 2, depending on polarization. So you have very high SNR, but you cannot work with a large number of spatial streams. The way to continue increasing the rate in this scenario is moving to higher order modulation like 4K QAM, and this is exactly what we're doing here. Again, the price, we need to work harder to achieve the very low EVM, but we're definitely doing that in Wi-Fi 7. Again, hand in hand, together with the large bandwidth is a preamble puncturing and multiple RU. And another question that I get a lot from customers, you can see I like talking to customers. Yeah. So another question that I get a lot from customers is, okay, Doron, you have this great 320 megahertz, this huge bandwidth, but this is Wi-Fi. This is unlicensed band, so we need to like compete for each one of these frequency slices. So what is the probability that I'm actually going to win the air on all of these 320 megahertz? And you can imagine, you guys are Wi-Fi experts, you can imagine that with the CSMA-CA mechanism of listen before talk of Wi-Fi, the probability that all the 320 will be yours in many scenarios is not very high. So the way to remedy this, the way to solve this is actually, and this is what I said, it's like OFDMA on steroid, is that in Wi-Fi 7, when you have preamble puncturing, let's say that we're considering this 160 megahertz, if this 80 megahertz is okay, but this 80 megahertz, you only have the upper 40 and the lower 40 is busy, you don't skip this 80 megahertz. Actually, you can transmit on all of these bands. So with preamble puncturing and multiple RU, you can identify the chunks in the frequency that are available, even if not continuous. And we have a lot of different patterns that we are supporting in Wi-Fi 7. So even if not continuous, like depicted here, you have a bunch of frequencies that are available. Then you can use them to transmit a very large bandwidth. So, for example, in this case, you don't have to like drop to 80 megahertz and totally kill the upper 80. You can work with 120 megahertz. Oh, okay. So this is a very big difference. Yeah, this is a very big, I think, advance of the Wi-Fi 7. You don't only increase bandwidth, so it doesn't matter if it's 320 or 160. The large bandwidths are also much more flexible, so that you increase the probability that you are going to get them. Okay, so we said 320, we said 4K QAM, and we said going hand in hand together with 320 is the preamble puncturing and multiple RU. So, you know, if you're taking a look from the bird's eye and you ask yourself, what was the key technology of Wi-Fi 6? So definitely it was OFDMA. I remind you my personal history with OFDMA. So definitely was OFDMA. What is the key technology for Wi-Fi 7? Definitely it's going to be multilink. And as I said, Oren will have a deep dive onto multilink. But like, again, from the bird's eye, multilink means that a station can communicate with an AP on multiple bands, multiple links on multiple bands at the same time. You don't have to like move from band to band. You can communicate simultaneously on the multiple bands. So, you know, the first thing that comes to mind of course, is I can create much larger throughput because I can aggregate the information on multiple bands, etc. But this is only one way to exploit, to use multilink. Another way is, for example, is to repeat the information in a smart way, and Oren will discuss it in much detail, is to repeat the information between the bands. And this way, you don't explicitly increase throughput, but you're working on is increasing your reliability or lowering your latency. So multilink is a basket of capabilities that is not aiming only at a specific target. We can use it in totally different ways. We will discuss it in much detail. But the capability of working simultaneously in multiple bands, together, you don't have to switch between frequencies, is amazingly important, and we will explain in much detail the different ways that we can use it, in different scenarios. So we discussed quickly Wi-Fi 7. I want to discuss a little bit about Wi-Fi 8, and then I'm going to, as I said, to have a deep dive into one of the, I think, most interesting, definitely hottest topic in today, in these days, because in standardization, from standardization point of view, Wi-Fi 7 just entering the market, but Wi-Fi 7 is, as I said, is already over, and now we're already deep into the research of Wi-Fi 8. So what is Wi-Fi 8 going to be about? So Wi-Fi 8 is going to focus mostly on UHR, on ultra high reliability. So when we guys as Wi-Fi research guys, when we think about Wi-Fi, we understand that if we want to penetrate all the amazing new markets of industrial and vertical markets that have a much more stringent requirements in terms of latency, in terms of reliability, and so on. If you want to compete, heads-on with applications like 5G, then definitely we want to move to much higher reliability, even though we are working on unlicensed band. So one of the topics that communicate directly with ultra high reliability is cell edge users. So imagine that I'm a cell edge user, this is me, and I'm communicating with AP1, but at the same time, I'm at a very similar distance also to AP2. Let's say D1 and D2 are almost the same. So what does it mean? It means that I hear my serving AP as strong as I hear the interference. I'm on the borderline, yeah, I'm on the cell boundary. So it means that my SNR in dB, is around 0. Yeah, is around 0 dB. So this is a very big headache in wireless communication. And one of the targets that UHR, the Wi-Fi 8, the BN, will try to solve is to solve specifically the cell edge user. And a natural way forward is to say, okay, if you just work in a plain vanilla way, yes, you're going to have the 0 dB SNR. But if these two access points, if access point 1 and access point 2, they can cooperate with each other, and there are multiple ways that they can cooperate, maybe they can create a huge advance in this aspect of cell edge users. So how can they cooperate? For example, they can coordinate transmission in OFDMA fashion, so that, for example, at the same time, AP1 will transmit here. This is AP1, and AP2 will transmit here. If they do that, and this can be done dynamically, yeah, of course, every transmission, every frame, we can play with it. If we can do that, then these guys remain orthogonal in the frequency domain. Doesn't matter. So of course, SNR will be much better. They can alternatively, they can transmit together like one super AP. This is called joint transmission. This is the most ambitious transmission scheme for AP cooperation. They can transmit like one super AP, in this case with 40x antennas, in a downlink multi-user MIMO way. And we'll discuss downlink multi-user MIMO in a minute. But they can also do something that is halfway much simpler and has much lower requirements in terms of synchronization and joint processing and so on. And they can do something similar to, let's say, spatial reuse. That one of them is transmitted to the STA, and the second one is trying to make sure that its transmission is avoided by the STA, for example, by placing spatial nodes with beamforming. Yeah. So we understand one that Wi-Fi 8 is going to focus on UHR, ultra high reliability, and we understand the second thing, that the cell edge user, which one of the biggest problems of if you want to reach the high reliability, the low latency, can be addressed if access points cooperate. So like again, from the bird's eye, Wi-Fi 8 is going to focus among other topics on access point cooperation to solve some of the biggest problems of wireless communication in general and Wi-Fi in particular. Okay, so having said that, having like this understanding of AP cooperation, I want to deep dive into coordinate beamforming. As I said, this is a very hot topic now in standardization. And like now we're just crafting the technology for coordinated beamforming. What I want to show you essentially is that coordinated beamforming as envisioned today in Wi-Fi 8 is broken. And I'm going to show you how Huawei is fixing it. Okay, so it's like an opportunity to, it's an opportunity for you guys to get under the hood, to see the technology from our point of view. So this part will be a little bit more mathematical, and but don't worry, later when Oren is starting his part, so no more math, no more equations, I think. So we will have a good blend of different types of Wi-Fi research. So in order to explain coordinated beamforming, in order to explain why coordinated beamforming is broken, I want to start with downlink multi-user MIMO. Okay? So I want to start with downlink multi-user MIMO. Again, downlink multi-user MIMO is today. Downlink multi-user MIMO is not futuristic. It is the present 11AC, 11AX, of course. So you know, think about it like that. I have an access point. I have, for example, 8 antennas. But I'm communicating with stations that usually don't have 8 antennas. These stations would usually have, let's say, 2 antennas, maybe 3 antennas. The most common number is 2. So how can I continue to increase capacity if the access point has a lot of antennas, let's say 8, and stations have a small number? So of course you can move to higher QAM, and we discussed and so on. But of course Shannon is going to limit you. Okay, you've gone to 12 bits per second per hertz. What's next? Yeah. So the way forward is in the direction of multi-user MIMO, and multi-user MIMO means that an AP will transmit on the same time and frequency resource to multiple stations at the same time. So this is like the key the key takeaway from this. And the question is, how can you do that? How can I transmit to station 1 while making sure that all other stations don't hear what I just transmitted, because it's interference? Yeah. So the way to do it is based on what we call precoding or beamforming. Precoding or beamforming. So let's dive a little bit into that. This is like the basic technology of Wi-Fi 5 and 6. So the key idea is precoding, as I said, and the point is that let's say that I want to transmit this vector S of information, of data. So in downlink multi-user MIMO, I don't transmit this vector. So if I just transmit it, of course, everybody is going to hear it, and I'm going to have a lot of interference in the air. The way that I like solve this problem is that I precode. I multiply this vector by some precoding metrics, and the precoding matrix job is to make sure that there is no interference. So for example, if I'm going to propagate through a MIMO channel H, this is the MIMO matrix. Imagine that if like W is proportional to H to the -1, so that the concatenation of H times H to the -1 is going to be identity matrix. Yeah. So we understand that, like, if I'm going to precode with the inverse of the channel matrix, then I'm going to make sure I don't have any interference. And in Wi-Fi, the station, they report the channel back to the transmitting AP. This is the feedback of Wi-Fi. So AP knows the channel that is going to propagate through, so it can precode with the inverse. Everything works perfectly. This is what's being done today. This is what's being done today, Wi-Fi 5 and in Wi-Fi 6. So of course, just making sure that there is no interference, it's not enough. We also want to make sure that your SNR is high. So when you take a look at the expression for the SNR, it is clear to see that you want to make sure that the inverse of H is small. How do you make sure the inverse of H is small? You don't transmit to two stations that are very close to each other. So if you have like another station right here, I will never transmit to these two guys at the same time. I would prefer to transmit to station 1 and to station 4 at the same time. So they have like big angular separation, meaning that the channels are decorrelated, which means that, of course, I can create good nulling and maintain good good SNR. So now let's add another layer to this, and let's say, okay, but what if my stations have more than one antenna? What if my stations have two antennas and I want to transmit two spatial streams to each? We're still in the current technology. I want to transmit two spatial streams to each. So this is great. You can say at first you can just do what you did before and transmit with the inverse of H, but of course we understand this would be a suboptimal solution. And a more optimal solution is making sure that we have like block diagonalization of H times W, meaning that I want to make sure that the transmission to station 1 doesn't reach station 2 and 3, but I don't want to invert inside each one of the stations. So mathematically speaking, what I want to say is that I want to say that W1 is within the null space of the other stations. And what I get is that, you see, like, this is the transmission to station 1, totally nulls out in the direction of station 2, totally nulls out in the direction of station 3. And mathematically, we're saying we are like inside the null space of the channels to the other stations. And in Wi-Fi, we can simply use the right singular vector of the channel matrix H. It's just the same as working with H itself. So it's perfectly aligned with the existing Wi-Fi feedback. Okay. So I think we can understand that. Now let's do something. Let's add another layer. And this other layer is saying, okay, what if I add more RX antennas? What if I want to keep two spatial streams to each one of my stations, but I want to add more RX antennas? And if I'm doing that, you know, we are trained to think that working with more RX antennas is a good thing. I added measurements. Working with more RX antennas should be a good thing. But if I'm like working in the same way that I did before, now I need to be in the null space of these 6 rows. It means that I need to have at least 8x antennas. Oh, now this is very frustrating because I did something good. I added RX antennas, but I suffer. And I suffer because I need more TX antennas. So Wi-Fi, again, this is still the background. Wi-Fi came up with a solution to this problem. And what Wi-Fi did, and don't be alarmed by the color code, of the SVD. What Wi-Fi did is said, okay, instead of trying to be in the null space of all the MIMO metrics, try to be in the null space only of the used SVD components. These are for example, in this case, we have 3 RX antennas. We have 3 components. Only 2 are used because I'm transmitting only 2 streams. So this would be the used components, the rank 2 matrix here. And I have another unused component, which is rank 1. So the Wi-Fi way says, you know what? Don't try to be in the null space of all the MIMO metrics. Try to be only in the null space of the used component, and this works perfectly well in the aspect of dimensionality, because okay, now I'm going back to 16 antennas. This is a great start. But it's not enough, because what I really care about is multi-user interference. So how does this scheme make sure that multi-user interference is taken care of, that I'm back at zero multi-user interference? So the good news is, I will skip the derivation. The good news is that if you're using this technique, all of this is called interference alignment. All of the interference in the air, doesn't matter how many streams there are in the air, all of them will modulate a single vector. This is interference alignment in regular Wi-Fi. And if all the interference is modulating a single vector, it is rank 1, it means that I need a single degree of freedom in order to totally mitigate it, using like MVDR or MMSC pre-coding. If you want, there is a nice video about it that I recorded approximately 1 year ago. Totally explains this angle if you're interested. But MMSC or MVDR would totally kill the interference to our back in zero MUI. Okay, so this is like a preliminary about downlink multi-user MIMO. And now we're going to coordinated beamforming. And the problem is that when you have multiple APs, like in coordinated beamforming, this game is going to happen for each one of them separately. So you will have a rank 1 interference from this guy and a rank 1 interference from this guy, so that the interference now would be rank 2. But the station still has only 1 degree of freedom. So it cannot mitigate the interference. And if you add more RX antennas, this is what I guess a natural thought. If you add more RX antennas, then also the rank of the interference would be double. So it doesn't, adding more RX antennas will not solve it. So let's just take a look at the simulation results. Take a look at what happens if I'm adding RX antennas. I get total collapse. Total collapse. Not very aligned with ultra-high reliability. Yeah, not very aligned with ultra-high reliability. But the message that I want to tell you is that our competitors haven't like recognized this. In order to recognize what is going to happen in the next generation of technology, you need to have very deep understanding of the underlying mechanics of the problem. So we had identified that what happened very well in downlink multi-user MIMO will not happen in Wi-Fi 8, and we will have complete collapse. But we don't stop there. We continue to a solution, and I will just say it in a few words, and if you have questions, I can dive deeper. But the concept, I think the concept is natural. It says, okay, station 1 knows that the interference from its serving AP1 is going to be modulated on its red unused U. So in order to mitigate it, it will apply project onto the null space of this guy, which is of course the used U, because these are part of a unitary, different parts of a unitary matrix. So you know what type of decoder combiner the station is going to use. So now make sure that W3 and W4 are in the null space of this equivalent matrix, which is smaller. It is a 2x8 matrix rather than the original 3x8 matrix. You want to be in the null space of this guy. And if you're in the null space of this guy, so of course you can do it with an SVD, but you can also do it with a QR. If you're in the null space of this guy, then the problem totally solved. Okay, so this is what happens if you don't work with Huawei. And this is what happens when you work with Huawei. So what I wanted to show you is that you saw it took more time to explain the problem than to explain the solution. And this is why some of our competitors haven't managed to identify the problem, because it's like deep inside the technology, deep down under several layers. So currently, this is a very hot topic in Wi-Fi 8. I hope that I managed to show to you that coordinated beamforming, which is a great technology to solve the big headache the cell edge user, has a very, very big problem that the current, let's say, envisioned implementation of it totally doesn't work. It is broken. We've managed to identify it. We've managed to come up with a solution. and actually not only come up with a solution that totally solves the problem, but also do it with lower complexity. And if you want, I can dive into the details a little later. So to sum it up, we are in very exciting times now. Yeah, so Wi-Fi 7 is turning from research into real life, and we are starting to look into Wi-Fi 8. Coordinated beamforming is one of the most important features expected in Wi-Fi 8. But as we showed, extending the downlink multi-user MIMO like magic to and philosophy to coordinated beamforming breaks, and we propose a lower cost solution. And currently, we are pushing this solution very hard into Wi-Fi 8 standardization. I'm very confident that we will totally succeed in that. So thank you very much for the time. And if you have any questions, I think after Oren's presentation, we can address whatever question you have. Shuya.
Hi. Okay. Any question? Or Mr. Oren?
Yes.
Continue.
Yeah, let me just share my screen.
Okay.
So is it okay? Do you see my screen?
Yes.
Okay, great. So hello, everybody. My name is Oren. And today, following Doron session, we will we'll cover some more specific aspects of the Wi-Fi, and I hope you will find it interesting. Okay, so what is the agenda for this session? So a little bit about myself. We will take a brief about Wi-Fi, how it grow through the generation, and what was the focus per generation, and I will give my perspective about it. Then we'll talk a little bit about the 5 gigahertz, the cellular versus Wi-Fi, and why they are different, and what we are doing in order to make it more reliable and deterministic, the Wi-Fi. And later on, the last part of this session will be focusing on one of the main features of the Wi-Fi 7, and this is the multi-link. So we will talk a little bit what is the multi-link. There are several flavors of that. Of course, Huawei AP supports all of them. And the last session we'll start and discuss actually how to deploy Wi-Fi 7 multi-link. Okay, it's not as simple as that. And I think this is our advantage as Huawei, that we're trying to solve these practical issues in advance and come prepared to the deployment. So who am I? So I'm dealing with Wi-Fi for the last almost 20 years. I was former assistant VP in Cellular. For the ones who are familiar with Cellular, mainly this is a cheaper vendor for residential. Then I dealt a little bit with video streaming over the internet and data centers. I was the chief architect in this company in embedded communication, mainly targeting US markets. I joined Huawei 7 years ago, and since then I'm focusing on reliability, Wi-Fi reliability, deterministic Wi-Fi, and so on. So I'm dealing with in the last for a few years with the multi-link AP cooperation, how to make it work in the Wi-Fi chipset, pushing stuff into the standardization of both Wi-Fi 7, and now we are working very hard to put our stuff in Wi-Fi 8. And I'm leading the research in Tel Aviv and on the Wi-Fi MAC, mainly focusing on reliability and deterministic Wi-Fi. And all of that, and you will see, it's not just slides and calculations. Behind that, we are running a very massive simulation, so we can, in advance, try to predict the problems and also provide the solutions to the product line. And at the end of the day, we are launching the product to you guys today after we anticipate what are the issues and put the algorithm already inside the product. This slide, I really like this slide. I'm trying to review the Wi-Fi through generations. So if you're looking about Wi-Fi 6 and already 7 versus what is the main target of Wi-Fi 8. So as we all know, whenever there is a new generation of Wi-Fi, we mainly see slides and flyers about additional throughput. How can we get more throughput and more megabit per second, gigabit per second over Wi-Fi? But nevertheless, all other topics are less dealt by the standardization. So we less hear about reliability, we less hear about how to have a quality of service over handover, and so on. And what we are trying to do is to close this gap in our product and not only and solely talk about max throughput. What the Wi-Fi 8 put as a target, finally put as a target, is to start and deal with this gap. This is the UHR, ultra high reliable. So this is, I hope that it's not only will stay on the naming, but also in the features that we will see in Wi-Fi 8, and we are trying to push such features into Wi-Fi 8. So I don't know if you asked yourself, so why Wi-Fi is not a reliable network? Okay, and why it's so challenging to have reliable Wi-Fi? But let's start with a network that defined itself as a reliable network. Okay, mainly the main issue in the 5G is not only a very fast network, but also a reliable network. But there's a huge and some fundamental differences between the Wi-Fi and the 5G/LTE. The cellular is working on the licensed spectrum, and this is the whole difference. Okay, it's fully managed by the operator, and we are paying for that. Okay, so if it's fully managed, you have a very easy access to the air. Everything is managed. The interference is managed. So by doing all that, I can fully control the frequency, fully control the medium, and I more easily can get a very deterministic and reliable network. On the other hand, Wi-Fi from day one put as a target is to be a low-cost wireless solution with simplified, distributed, opportunistic approach. Okay, unlike the cellular, which is very expensive, both for the customer and also for the service providers, the Wi-Fi is a low-cost solution. And for a choice, it chose to work on the unlicensed spectrum. Okay, again, very low-cost solution on the 2.4 gigahertz, 5 gigahertz, and on Wi-Fi 6.6, the sub-7 gigahertz. So when you're working on the unlicensed spectrum, you need to follow the regulations in the United States, the FCC, and in Europe, the ETSI, mainly following the rules how to access the medium and be fair with other devices that using the medium as well, but not belonging to the same vendor. So you need to play a fair game. And how do you play a fair game with others? You're doing CSMA-CA. This is the carrier sense multiple access with collision avoidance. A very long name, just saying, okay, you need to listen before you're addressing the medium, and if you're hearing somebody else, you need to stop, okay, and don't transmit. And now you need to count a random backoff before you are transmitting again, and by that, everybody are taking random backoffs, and hopefully, statistically, it will work. Okay, so by definition, CSMA-CA is a opportunistic approach, not a deterministic approach, and this is the main difference between cellular networks and the Wi-Fi networks. So let's try to see how it works in practice. So if I'm an AP and I want to transmit to a station, so I'm accessing the medium, and let's assume the medium is free. So I'm starting the transmission, and I'm expecting to get an ACK at the end of the transmission from the destination. The other AP, AP2, is receiving also this transmission, is hearing and sensing the energy, so it's stopping his activity, okay? And he's stopping the backoff counting. and he's waiting to the end of the transmission. And at the end of the transmission, he's taking a backoff again and continue counting. And if I'm AP1 and I want to transmit again, so I'm taking another backoff. Hopefully, we'll take different random backoffs. This is the whole issue about taking randomized backoff. And then let's say AP2 is winning there, and so on and so on, and we are getting, in statistically opportunistic manner, a fairness between all devices. Okay, so looks good, right? But it's hiding a lot of potential risks. One of them is what will happen if, and it happens, that the two of us will take the same backoff, okay, or different start time, but it will end the backoff counting on the same time. We will sense the air, the medium is free, and both of us will go and transmit exactly on the same time. So if we transmit in exact same time, the receiver will not be able to successfully receive the required signals, and we will get an error. This is, we call it RX collision error, because there is a collision between these two devices on the receiver. And now what the standard is saying, okay, that can happen, but in order to avoid the next collision, now each one of the devices need to take a different backoff and extending the window of the randomization. So now we are paying with more delay. Not only we pay the delay for the failures transmission over here, both devices, more than that, we are now paying another fee, and we are taking a larger backoff. So we try to avoid the next collision, and now we need to do a retry, not go on and transmit the new packets. Okay, so this is just a simple example showing why it's not deterministic network. Okay, one is we might be colliding with other devices, and even in this example, that everything is working perfect, right? We have no collisions, no retries. Again, I'm suffering from unexpected delay as AP1 because I now need to wait for AP2 to finish its transmission. So I didn't take it into account, right? And this is just an example of two APs. Of course, in enterprise deployments, we are talking about tens of APs working on the same channel. So of course, we cannot, it will be very hard to get a deterministic KPIs for either delay, jitter, and so on. So why we think that Wi-Fi 7 is going to make things better? And this is, I think, one of the main difference between our approach and maybe other companies. We are looking on Wi-Fi 7 as an opportunity to make the first step into reliable network, and not only about max throughput, okay? When you are talking about Wi-Fi 7, we want to take it into the reliability world rather than solely about throughput. Everybody will get the throughput, same as Huawei, but we want to make the algorithm and make the network more reliable. So how can it help us? So we all remember this example with a single link, but now if I a multi-link AP and I have another channel that I can access, so if I'm an AP2, okay, and I'm taking the medium now, an AP1, and as in the previous example, wanted to transmit, but it's all blocked, so it's still blocked on this channel, but he has another channel, and most likely the other channel might be free, so I can take a chance of that. Of course, I'm doing the same CSMA CA flow on the second channel, but statistically, not both of them will be occupied. Okay, maybe I have 3 links, not only 1 or 2. So statistically, I'm decreasing the probability that I will be blocked, and I will be able to transmit my data in the time that I really need to transmit it. Okay, so here if AP1 is blocked, you can use the other channel, AP1 on link number 2, and just simply transmit it, and so on and so on. And the same manner for AP2, when AP1 is transmitting, it can go to the other channel, and so on and so on. Okay, so as we can see, multi-link is not only about increasing the throughput. Of course, it is a byproduct, a trivial byproduct of the multi-link, but it's a very important tool in order to get more reliable network So as you can see, also reducing the amount of collisions because splitting the data between channels and so on. So all in all, it's a very important tool in order to increase the reliability and make the first stage into a more deterministic network. So what is multilink? We hear these terms a lot, and you will hear these terms a lot. I want to shortly tell you about the architecture of the multilink and two leading modes of multilink communication between an AP and a station. So this is taken from the standard. So basically, multilink is on the file layer, okay, on the physical layer. On the software layer, we see all links as one AP. The standard call it affiliated APs. So the upper layer, the software, doesn't care about how many physical layer it has. It's just taking the opportunity to use them. And also in terms of the networking, okay, when the networking is looking on this AP, which is a multilink, it doesn't know that there are many links that this AP is using for the medium. From the network perspective, there is a single entity, and this is a multilink AP. Okay, it doesn't care about all the affiliated APs. So you have still a single MAC address, a single IP for this access point. Okay, so in terms of networking, this is transparent to the network, and this is very important for the simplicity of the deployment. So what are the options, okay, of multilink? And let's, for the simplicity, take only two links. So we can take the 2.4 gigahertz plus the 5 gigahertz, or the 5 gigahertz low band with the 5 gigahertz high band. This is quite risky because we need to have a very good RF separation between these close frequencies, right? Or we can take a more relaxable and more better mode, which is taking the 5 gigahertz low and the 6 gigahertz band. And in Europe, we are quite limited with UNI 5 only, okay? And again, we need to have a very good RF separation because 6 gigahertz low and the 5 gigahertz high is just extension of the 5 gigahertz high. Okay, so these are our options. The first one, which is the full-blown, it's an STR mode. It means that I can transmit and receive on the same time between the two links, and this is quite challenging. Okay, because if I'm transmitting, let's say I'm an AP and I'm transmitting on link 1, okay, there is a leakage of the RF signal between link 1 to link 2, even though I have, I'm working on different frequencies and different bands, yet there is a leakage of the signal between these two links, because here, when I'm transmitting with very high power, right? Because I want to get for distant stations, but this receiver is quite close. So it's getting the signal in very high level. So it's blocked and cannot receive anything from the station on this link, for instance. But in STR mode, the ones who support that have a good RF separation between them, and it works successfully as it's working in Huawei AP. So this is an STR mode, and this should be supported also by the station. So on the AP side, there is enough real estate in order to do that. On the station side, this is quite challenging, okay, mainly on the cell phones, to have a very good RF separation between the two links, and this very tight real estate, and when we are very sensitive to the cost, this is a huge challenge. And many of the cell phone vendor will not support that. So in order to still support multilink on these cell phone devices, there is another mode. It's called EMLSR, Enhanced Multilink Single Radio mode. And this is more relaxed mode and letting a lot of grace to the station. It means that I'm working only on a single channel per TX opportunity with the station, but I'm still keeping the right to use each one of the channels whenever I want. So how it works. So if, let's say, here it's an uplink transmission. So if the station wants to send something to the AP, it's sending a signaling to the AP, a multi-user RTS. okay, or vice versa. Let's do it from the AP to the station. So the AP is signaling to the station, I'm going to transmit you on this link using the multi-year RTS packet, okay? Now the station will signal back the CTS and we will send the data, okay? But the station on this, in this mode, will know that will be no, the link number 2 will not work when link number 1 is working. And more than that, and more important than that, the AP scheduler will know that. So when it's transmitting to on link 1 to the station, it will not transmit also in link 2. And by doing that, the station can have, it's not a real single radio, it's a radio and a half. So it have a single radio, full radio, transmit and receive on this link. And on the other link, it just need to listen and wait for a signaling for the AP in case he wants to work on link 2. And if it's getting this MURTS on link 2, so it's switching. So it's putting the full radio on link 2 and the half radio on link 1. And by doing that, we have enough grace on the station side, and we're less concerned about the RF separation between these two links. So most likely when you will see a multi-link station device, it will support the MLSR rather than the STR. Only high-end devices as a station will support that. AP side should support both modes. Okay, so now that we have a good understanding about the multi-link and how it works and what are the limitations and so on, let's start and analyze a deployment, an enterprise deployment with a multi-link, okay? And we'll see that it's quite challenging, okay? So, and it's all, like everything in life, it's a trade-off. We need to pay something in order to win something. So what we're going to pay? So if so far for each AP we allocated only a single channel, now when we have a multi-link, and just for the simplicity of this discussion, let's discuss about 2 links. So we need to allocate 2 channels per AP. So if it was too complicated to allocate a single channel per AP, now we need an algorithm to allocate 2 channels per AP. Okay, so this is one thing. And this is not only about the algorithm complexity, but it's also limiting, okay, ourselves, and we have a limited list of channels to play with because we need to split it between the 2 links, okay? And it means that we more frequently use the same channel per AP, and we will see it in a minute. So as I explained, more APs on the same channel, it's more collisions, more time sharing, so it's not coming from free, this multi-link. And if we are using the frequency more often, it's not only increasing the number of APs per channel, it also making the distance between APs more closer. And what is the impact of that? The interference level that we will sense from these APs is much higher than we had before when we have more distance between the APs. So when we analyze a multi-link deployment, we need to take these trade-offs into consideration. And this is exactly the exercise that I'm going to do with you guys, okay? So let's think about it. So if I'm deploying a single link like we did with Wi-Fi 6 so far, I have 12 and 20 megahertz channels. Let's, for the simplicity, take 20 megahertz channels. I have 8 on the low channel and 4 on the high band. Total of 12 channels. If I'm looking on 20 APs grid, it means that I'm repeating myself on average on each 1.5 APs. Okay, now let's see what if I will try to deploy multi-link only on the 5 gigahertz. Okay, so I need to split the channels between the links. So one link will get the low band and the other link will get the high band. So now I'm playing with 8 channels and 4 channels. So on the low band, I will repeat myself 2.5 times on average. And on the high band, on the 5 gigahertz, oh, now it's already 5. Okay, so this is not a nice number, and we'll see. Now there is a question. So is it worth it, okay, to take a single link or to take a multi-link? We will discuss it, okay? But we already know that Wi-Fi 6 is saving us, okay? And there is the 6E with the 6 gigahertz, and lucky us on Europe, it's available. So we have an opportunity to play with the 5 gigahertz low band and the 6 gigahertz, right? So now we have 8 channels from the low band. Okay, we cannot use the high band, it's too close to the 6 gigahertz, okay? And we have, okay, take a look here. In Europe, we have 24 channels of 20 megahertz. Okay, this is nice. Okay, so we can play with these ones. Now let's try and evaluate the performance of each one of these topologies. Okay. Okay, so let's try and analyze the topology. Okay, and step by step, we'll see the impact of the multilink and the potential gain or negative gain that we will get from it. So this is the 20 APs grid, okay, from 0 to 19. Each one of them, just for the simplicity of the use case, have a single station, okay? And if I'm using a single link, you can see that by the colors, I'm not repeating myself too much, okay? There is a 20 meters between AP and a station, you assuming a cell of 10 meters, okay, with overlapping and so on. So this is quite nice, okay? So I'm not repeating myself too much. And the impact of that is that the same channel OBSS is quite far from me. So it's good for the decade of the signal. So the signal to interference ratio is around 20 dB. Okay, it gives me a lot of grace. Of course, I cannot work in 4 QAM like what Doron just mentioned to you guys, right? It's not, what is Doron, 38 or 32, I don't remember. But so we cannot reach it, but we can certainly use a very nice modulation and very nice throughput with that one. Okay. But if we will deploy the 5 gigahertz low and high, we'll see now that we need to repeat ourselves more often. We have 4 channels for the high band and 8 channels for the low band. Okay. So as you can see, we are repeating ourselves much more frequently, mainly on the high band. So we need to evaluate if it's worth it or not. Okay, and not only we increasing the number of APs, but also our SIR is much lower. If we had 20 dB before, now we have more APs on the grid, which are much closer to us, and now we have only SIR of 15 dB, and this is quite important. Okay, so we're increasing the number of APs. We have bad or worse, where increasing the interference, and also while increasing the number of APs, we're increasing the collisions probability between APs, leading to packet error over the air, retries, and so on. So not sure we will get better performance than a single link. But the third option, and I believe that everyone thinks this is the preferred one, is the 5 gigahertz low with the 6 gigahertz. So we are gaining from all modes. Okay, so we have a lot of frequencies on the 6 gigahertz, and we can use the low band on the 5 gigahertz. Okay, so we are winning from all sides. So now on the 6 gigahertz, we have 24 channels, so we have a very good SIR. The APs that repeat themselves are very far from each other, so this is good for us. Okay, now that we understood the picture, let's start and see the performance. And we will start with the KPI that everybody used to talk about, and this is the throughput. Okay, so we took some moderate MCS, okay, MCS5, 2 spatial streams. All in all, it's a fire rate of 130 megabit per second, okay, per station. This is the fire rate, okay? And as you can see, I didn't took it to the edge. I'm not looking for the max throughput. I want to see how the system is behaving when it's capable to take the throughput and deliver all the packets end to end. And then I will deep dive to the other KPIs of the reliability KPIs. So you can see that if the system is not challenged on a very low load, so single link and multi-link have quite the same performance. If I'm increasing the load, the throughput per station, so we are starting to see a difference between the single link, okay, on the 5 gigahertz and the multi-link, okay? And still, there is no huge advantage of 5 gigahertz low and high or 6 gigahertz. We are managing that okay. Now we will increase the throughput and challenge the system with high load, not overloading, but high load. So we can see that the single link is stacking over here. But again, the multi-link, all modes are performing quite good, okay? So this is just in terms of throughput. and that's it. But it's also nice to see what is the contribution, okay, of each one of the links. Okay, we want to see the multilinking that is working. Okay, it's not something, it's not a magic. We want to test it and see how each one of the links is contributing. Okay, so in this example, the 5 gigahertz low and high, as expected, we can see link 1, which is the 5 gigahertz low, is contributing a lot, much more than the high band, which is more crowded. Okay, so it's making sense to us when we're analyzing the network. Okay, this is just to verify ourselves and see that it's making sense. Now let's move forward for me, the most interesting KPI, which is the delay. Okay, so this is a CCDF delay. Okay, on the x-axis, it's delay in millisecond, and the y-axis is the percentage of packets and traffic that can meet um, the delay, this delay on the x-axis. So let's start with the single link. So we can see, as expected, that as I explained about the EDCA and so on, using single link on Go, although I have 12 channels, still in terms of delay, I'm quite limited, okay, because I have no opportunity, if the channel is free, to use another channel. Now let's try and evaluate what is happening on the multilink. So as we can see, if we're using the 5 gigahertz low and high, we have better performance than the single link, much better performance. You can see the delay reduction quite clearly, okay? And if you're using, and this is the difference between STR, this is the multilink STR, which of course it's much more effective, versus the EMLSR that we're spending time on multi-SRTS, and the impact of the delay is quite clear, but yet we are gaining a lot versus the single link. And of course, the winning topology is using the 5 gigahertz low and the 6 gigahertz. And of course, as you can imagine, mainly to do the 6 gigahertz. Okay, so you can see a quite impressive performance in terms of delay while using the 5 gigahertz low and the 6 gigahertz. Okay, so now let's take it to the next level. Okay, we evaluate the 6, we understand that the 5 gigahertz low and the 6 gigahertz, this is the best practice topology. But there are more options with the 6 gigahertz. And now let's see whether should we start with the 20 megahertz on the 6 gigahertz, okay? Or we can go and increase the bandwidth of the network to 40 gigahertz or 80 megahertz, okay? So again, if we look on the spectrum, we have 12 channels of 40 megahertz and 6 channels of 80 megahertz in Europe, okay? So now the question, and we should ask ourselves, okay, what is better, okay? What will give us the best KPI? And remember, my KPI is not throughput, okay? I'm not looking for the brochure with a high throughput. I'm looking for exactly what you guys are looking for, the reliability and the quality of service for the end customer, okay? So we'll try to evaluate now what is the winning topology in this example. And of course, we can evaluate each one of the deployments. But in this example, we will try, based on what we did so far, to evaluate what is the best practice. So I think you already know me, and I'm starting again from the topology and from the physical layer, okay? So if we are using the 40 megahertz, we will repeat ourselves a little bit more, okay? Than using just the 20 megahertz. Okay, this is one thing. But if we will shift into the 80 megahertz, now we have only 6 channels. So we are back to the 5 gigahertz issue. So we are repeating ourselves every 3 times. Okay, so let's see the impact of that, whether it's worth it or not. Okay. So again, if we look on throughput, okay, we can see quite easily that if we increase the throughput a little bit when we shift to the 6 gigahertz. So all modes can deliver the required throughput in the same manner, okay? 80 megahertz, 40 megahertz, and 20 megahertz. But in terms of delay, and this is the huge surprise, okay? We can see that 80 megahertz is given worst performance. It's not worse, it's slightly low performance versus the 40 megahertz. So we can see that 20 megahertz, although it has a lot of channels, the TX duration on 20 megahertz it's quite long versus the 40 and the 80 megahertz. Okay, this is why we are getting this huge delay on the 20 megahertz, both on 5 gigahertz and 6 gigahertz. But the interesting stuff is what is the difference between 80 megahertz and 40 megahertz? Why 40 megahertz is providing us better delay than the 6 gigahertz on 80 megahertz? Okay, and the answer is in the retries. Okay, just as we talked on the beginning of this session, we explained that when we're adding more and more APs on the same channel due to the CSMA-CA, we're adding more collisions and more time sharing. And here we can see that on the 6 gigahertz, when using 80 megahertz, we have more APs on the same channel, so we're increasing the probability of collisions. And this is something very have a very bad impact on the whole system. Okay, so we suffer from a lot of packet error rate. This is the success rate. It means that the packet error rate over the air is between 10 to 30%, and I need to do several times of retries in order to deliver the packet sometimes. Okay, so when I'm using the 40 megahertz, I can see that I'm working with much more stable environment. Okay, quite as using 20 megahertz. Okay, almost the same. But the difference between the 40 megahertz and the 80 megahertz is very important. And if you remember, we talked about the EDCA and the collisions, and this graph, I really like that. It's representing the times of collisions. So usually the contention window in which we take the random back of per TXOP is starting with a default of 15 slots. But if I have a collision, as I said, I need to increase it by 2. So it's increasing to 31. And if I have another collision, to 63 and 127. Okay, so you can see if I'm using the 80 megahertz, and the green one is the 80 megahertz, the amount of collisions is growing and rapidly happening all the time. So this is coming along with the retries. Okay, so this is have a very huge impact of the delay. Versus if I'm using the 40 megahertz, I can see sporadic events of these kinds of collisions. Okay, making sense, but the impact of that on the network is neglectable. Okay, so now we understood why the 80 megahertz is less good than the 40 megahertz in terms of the delay, although in throughput they're providing the same exact throughput. Okay. So summarize all these things together. Okay. So we can see that multi-link is the leading technology in terms of the system of Wi-Fi 7. Okay. We discussed the trade-offs while using multi-link, and if we are aiming for more reliable network, so multi-link is the right way to go. But, and this is the but, you need to know what you're doing. Okay, you just not deployed multi-link as is. Okay, otherwise we get worse performance than even a single link. And hopefully, while you deployed the Huawei multi-link, you will discover that we put a lot of effort on the algorithm in order to make it as expected and get the most of that, mainly for the reliable network. Thank you very much.
Okay, thank you very much, Mr. Doron, and also to Dr. Doron for this great presenting today. Explained a lot of interesting technical details, and the formulas brought back memories of my school days. Okay, it's question time. I saw there a question. How does APSTA decide which link to use traffic in EMLSR?
Okay, so there are two methods, okay? And this is also something that over generations, Wi-Fi is making a progress to more a managed network. And this is based on, already in Wi-Fi 6, we have the trigger-based uplink, okay? So the AP can trigger the station which link to transmit. So the AP can control that. Of course, the station can transmit by itself in unmanaged mode, and use the same multi-user RTS on the available link, so the AP knows that it's expecting to get traffic over this link, so we will not transmit on the other link to this station. But the common usage will be with trigger-based uplink, so the station will be managed.
Okay, thank you.
Maybe we can address questions orally. Yeah, if guys can just talk.
Yeah, I'm not sure if other ones can talk. Okay, let me check. Sorry, not familiar with this system. Okay, if you can talk, please make free to ask questions, or you can type here. We still have some time. Okay. I think if no more questions, so this is the end of today's webinar. Thank you everyone again, and hope everyone found great value here. And if any questions, I think you can send a mail to us, and we will glad to answer.
We will answer any question, and we'll usually very available, and we look forward to your great questions.
Yeah.
Thank you very much.
Thank you again, Mr. Oren and Dr.